So we have one section left before we start doing a review quiz tomorrow. All right. Our topic today is normal distributions. We are going to look at what it means to be a normal distribution and how we can use that to analyze our data. Okay. How many have heard of a normal curve? A few of you? Okay. All right. So we have a couple different kinds of probability distributions. If it is a discrete one, we talk about finite number of possible events or values. Typically what you would see on your graph would be bars. They're going to use the height of the bar to represent that probability. Okay? When we have continuous probability distribution, we use that for any value in an interval of real numbers. Large data sets of discrete values have approximately a continuous distribution. In other words, if I collected enough data, my top graph with the bars could resemble a normal distribution, a continuous distribution. All right, and for this one, what you're going to see would be that bell-shaped curve, a normal curve. Okay, so again, if our bars are fitting a normal distribution, we could kind of fit a normal curve to that. Does that make sense? So we're going to have a few examples where we use the height of the bar to help us figure out the probability of being in that interval. And we're also going to look at how we figure out under a curve like this. Many common statistics, such as human height, weight, or blood pressure, gathered from samples in the natural world, tend to have a normal distribution about their mean. In other words, if I collected just a random sample, right, of all American males between the age of 40 and 50, okay, we could fit that normal curve to it. A normal distribution has data that vary randomly from the mean. The graph of a normal distribution is what we call a normal curve. This next picture has a lot of information in it. We're talking about how we divide up our normal distribution. We refer to it as the 68, 95, 99.7 rule. Go ahead and circle that. We're going to need that a little later in our notes as well. And what that means is that 68% of the data fall within one standard deviation of the mean. Do you remember yesterday when we did our number line and we put the little x's above? And then we divided it up, right? We figured out where one standard deviation, 2, 3, and we said all of our data lands within 2 standard deviations. Okay? We're talking today about normal distribution. So if we had that normal curve shape to our data, which we didn't yesterday, okay, but if we did, we're saying 68% of our little x's would have landed within 1 standard deviation of the mean. 95% are going to land within 2 standard deviations. And 99.7 will land within 3 standard deviations. So what we can do is we can take our graph, we start out with a normal shaped bell curve, okay, and we're going to divide it up into intervals. So our first one would be the mean. We're going to split it down the middle. So for a completely normally distributed set of data, your mean and your median would be the same. They'd have the same value. Okay? The 68, 95, 99.7 rule tells me that 68% of my data has to be within 1 standard deviation of the mean. So I am going from here, -1 to +1. In this chunk, I need 68% of my data. All right? And our normal curve is nice and symmetric, so we would split that in half. We'd say we have 34% on either side of the mean value. Does that make sense? Okay. Then it said that 95% of our data has to land within 2. Okay? Well, If we have 95% of our data landing within 2, we've already accounted for 68% of it in those 2 middle chunks. What do we have left over? 95 minus 68. 27? And if we took that 27 and we split it in half, what would we have? 13 and a half. That's where these numbers are coming from. Okay? As I make them unreadable. Okay? So we have 13.5% split in each of those chunks. So if we add it up, 13.5 plus 34 plus 34 plus 13.5, that's our 95%. Okay? Our next bump out is going to 99.7. If we take away the 95 that we've already accounted for, we have 4.7% left to divide up. We're going to put half on each side. Half of 4.7 is 2.35. That's where these numbers come from. Does that make sense? That gave us 99.7% of our data. What do we have left over? 0.3%. We have another 0.3% that we have to account for. Splitting that in half, so we're talking 100 minus 99.7 is 0.3. Splitting it in half, we would have 0.15. That's the little chunk that you're going to have on the ends. So go ahead and add that in. That now accounts for all 100% of our data. Okay? A normal distribution has a very nice symmetric bell-shaped curve. That's important, that it is symmetric, so we can evenly split those percentages. All right, so we're going to look at both situations. How do we get information from a bar graph? How do we get information from one of these normally distributed curves? It says sometimes an extraordinary factor affects data sets. For example, a coin might be weighted unevenly so that heads tends to come up more frequently than tails. That is going to skew your data. Yes? If you had a fair coin, right, equally likely that it's going to land heads and tails. But if it's a weighted coin, that changes it. Okay? It's no longer equal. So what we have in the center, our center picture, is a typical normal distribution. Right? Nice symmetric bell-shaped curve. The first picture we refer to as positively skewed or right skewed. Basically what we're saying is that something is pulling this little tail further up than it should be. Okay? On this third picture, we have a negatively skewed or left skewed, meaning the tail is being pulled towards the left side. Okay? Could an outlier do that to my data? Yeah. All right, I could have a test score that ends up being normally distributed, but there's just one person that's just way out there. Okay? That could drag that curve. All right, so our first one, we have a bar graph. They've overlaid a bell-shaped curve to it. So you can kind of see that even though it's in bar graph format, it does resemble a normal distribution. Yes? Okay. A couple things to notice. The x-axis of this graph, the horizontal axis, has the weights, and they are in intervals. So each bar represents an interval length of 10. The vertical axis is listed as percents. Okay? So what we want to do before we even get started on this is we want to figure out the height of each bar. Okay? So for this middle tallest bar, we're a little above 40, but doesn't look quite halfway, so we're going to say that's 42. Okay? The next bar on either side of that, what would you estimate? 23? Okay? Our next bars, they look to be about 5, right? Looks like it's hitting that mark. How much is that? How much have we added up here? 42 plus 23 plus 23 plus another 10. Where are we at? 98. So we still have 2% left. So does it look like about 1% on either end? This little teeny bar? Okay. So we've accounted for 100% of the female brown bears. The question says, the red curve shows how the weights are normally distributed evenly about the mean of 115 kilograms. We are going to need that mean value, so go ahead and circle that. We're going to have to come back to that in a few minutes. Approximately what percent of female brown bears weigh between 100 and 129 kilograms? So let's think about which of the bars are we talking about here. From 100 to 129. We're going from here to here. So those three middle bars. So could we add their heights to get the total percent that are in that interval? Okay, so we need to take 23 plus 42 plus another 23. What do we get? All right, so we're saying 88% of the female brown bears weigh between 100 and 129 kilograms. Make sense? All right. Our next question says, approximately what percent of female brown bears weigh less than 120 kilograms? So going back to my picture, now I'm talking about being lower than this mark, right? So what are some options for me to figure out that value? Can I add all the bars below that green mark? Yes. What's another option? Okay, so I could take 100% minus the 3 bars that are above it. That might be a little faster. Yes? So you do have some options. Remember that the whole thing represents 100%, right? So you can subtract what you don't want from 100 to get what you do want, whichever seems easier for that particular question. All right, so we would take the 42 plus 23 plus 5 plus 1. If we were going to add, we would take 100 minus 23 plus 5 plus 1 if we were going to do it the other way. Okay? What do we end up with? 23, 5, and 1 gets us 29. What's 100 minus 29? Okay, so we're talking 71% of the female brown bears weigh less than 120 kilograms. Okay. The next question says, the standard deviation in the weights of female brown bears is about 10 kilograms. Approximately what percent of female brown bears have weights that are within 1.5 standard deviations of the mean? Yesterday we kept going up by 1 standard deviation increments, right? Now they're saying, what if we went up 1.5 standard deviations? What's that new interval? So what is 1.5 standard deviations? If a standard deviation is 10. We're talking 15? Okay, so they're talking within 15 kilograms of the average, which means we are going to take our average, I had you circle that earlier, that was 115 kilograms, and we are going to add and subtract that 15 kilogram increment. What do we end up with for a low value, and what do we end up with for a high value? Okay, so we're looking at being between 100 and 130. Okay, so let's go back to our graph now. Which bars would that represent? The 3 in the middle? So it's the same thing we calculated in part A, right? We got what for an answer? 88%. Yep. Questions about that? So given a bar graph, could you use the heights to help you figure out your total percentages for each interval? Okay. When data are normally distributed, you can sketch the graph of the distribution using the fact that a normal curve has a symmetric bell shape. So for this question, we are given population of male European eels. Their mean body length is 15.7 inches. One positive standard deviation above that would be 18.5 inches, and one standard deviation below the mean would be 12.9 inches. With that information, could we fill in our graph? Could we figure out what those marks should be at the bottom? So instead of bar graphs now, we have that normally distributed curve, okay, a normal distribution. What did they tell us the mean was? 15.7, okay, I'm going to mark that down here. What did they say the length was if we were one standard deviation above? 18.5. So this first black dotted line that I just wrote 18.5 by, that is one standard deviation above, correct? I gave you kind of the template to use. On your homework, you're not going to have that. You're going to have to draw this out, okay? So I do want you to label, all right? Your middle mark is going to be your mean. Then you have plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations. You can use the sigma notation, all right, instead of writing out the words. But you should label it that way. All right. What did they say for -1 standard deviations? All right. If we have this much information, could we figure out our standard deviation? How much are we going up and down from that average? Okay. So you took 18.5, you subtracted 15.7. Yes? So our standard deviation is 2.8. All right, I'm going to go ahead and pause the recording. I want you guys to fill in the rest of the numbers on the bottom. All right, let's move to the top end here. 18.5, if we add 2.8, right, we're going up in increments of 2.8. What would we get? All right, go up again, another 2.8. All right. Going towards the negative side, we said we had 12.9 there. What's the next one down? Okay, and? All right, questions on that? So you can label your numbers at the bottom, yes, and you can label your vertical breaks in your graph. Okay. So for this one, it says a population of female European eels has a mean body length of 21.1 inches. I'm going to put that here, 21.1, our mean. The standard deviation is 4.7. So can we calculate the rest of our numbers? Okay. Adding 4.7 to 21.1 gives us, adding another 4.7. Okay, somebody else add another 4.7. Thank you. All right, subtracting 4.7. What do we end up with? 16.4. 11.7. And? Okay. What would we title this graph? Distribution of body length for okay. All right. Questions on any of that? So this is the first part of our process when we talk about a normal distribution. Remember how we split up our 68, 95, 99.7? Okay, that's the next piece. We're going to add that information in. When you show a probability distribution as a bar graph, the height of the bar indicates the probability. When you show for a normal distribution using a normal curve, it's the area between the curve and that interval and the x-axis. In other words, this chunk here, right, would represent the probability of being in that interval from whatever here to here is. Does that make sense? Okay. So for this question, it says the heights of adult American males are approximately normally distributed with a mean of 69.5 inches and a standard deviation of 2.5 inches. So let's get our numbers on the bottom filled in. We have a mean of 69.5. What did they say our first increment would be? What was the standard deviation? 2.5. So if we take 69.5 and add 2.5, we're at 72. Okay, add another 2.5. Add another 2.5. Okay, to go on the other end, we have to subtract 2.5. So 69.5 minus 2.5 is 67. Subtract another 2.5. And subtract another 2.5. Yes? All right. Label your vertical breaks. We have +1 standard deviations. This would be +2 standard deviations. And this over here would be +3. Going down, we are at -1 standard deviation, -2 standard deviations, and -3 standard deviations. Okay? If you were graphing this, drawing your normal curve all by yourself, a couple things to keep in mind. When you get to this +3 standard deviations, the height of my curve, the height of the red line, or the red curve here, is close to 0, correct? On both ends. By the time you get to the third standard deviation, you're pretty much down by 0. At the first standard deviation, okay, we are a little bit above halfway to the top, the highest point. So if you picture being your average being your highest mark, we are just a little bit above that height. So you can kind of draw it in more accurately. Okay? Now, we're going to go back in and we're going to fill in those percentages. What was our rule? The 3-number rule that we had? 68, 95, and 99.7. Yes? So 68% has to be within 1 standard deviation. We're going to split it up. We're going to put 34 in each one, correct? Then we had the next jump goes up to 95%. We've already accounted for 68, which means we have an extra 27%. We split that up, and we are going to have 13.5% in each of these chunks. Then we go up to the 99.7, which means we have an extra 4.7% to split up, which means we have 2.35. And our last little piece, the little tails, 0.15%. All right, so the question that we're being asked, what percent of adult American males are between 67 inches and 74.5 inches tall? So based on the numbers I have at the bottom here, we want to go from 67 to 74.5. So we're talking from here to here, correct? So it's the lightly shaded section on my picture. All right, so just lightly shade in that little portion. How are we going to figure out how much that is? Add them up. We have 34 and 34. So 68%. Plus another 13.5. What's 68 plus 13.5? So we would say approximately 81.5% of adult males are between 67 and 74.5 inches tall. Okay. Our next question says, in a group of 2,000 adult American males, about how many would you expect to be taller than 6 feet, or 72 inches? We want to be taller than 72. Can you see where we're looking on our graph? We want to be from here on up, correct? What's a quick way we could figure that out? So we could add the 3 little percentages that I just marked off, right? We could add those 3 together. Another option? That's faster than saying 100% minus all of the other ones, correct? Okay, but there is one that's even faster. How much is to the right of your average? 50%, right? So we know that from my average mark up is 50%. The only chunk we don't want is the 34%. So that's another way we could calculate it. Doesn't matter to me which way you use. All right, so what did we have? 50 minus 34 would be 16%. Or you could have added your 13.5, your 2.35, and your 0.15. Either way, you get 16%. Is that the answer to the question? No. What did they ask me?
How many out of 2,000?
How many out of 2,000 would we expect to be over 6 feet tall? So we are saying that there should be about 16% of those people. What is 16% of 2,000?
320.
So we could say about 320 would be taller than 6 feet. All right, I'm going to pause the recording. I want you guys to try the last question. All right, checking your numbers. I did title this one Algebra 2 Final Scores. We've got our percents broken down in the green ink, and at the bottom we have our intervals, okay, for test scores. I've also labeled each one as to which standard deviation increment it is at. Okay? So the first question said, what percentage of students who took the test scored above 180? So now we're looking at from here on up. Okay? How would we do that? Add them together. Fastest way. All right? So we have 2.35% plus 0.15. So we're at 2.5%. Okay? Part B says, if 250 students took the final, approximately how many scored above 135? So above 135, what's a quick way we could figure that out? So 50% gets me to the middle, correct? So if I take all of the stuff to the right of that, that's 50%, plus I need an extra 34%. Okay? So 34 plus 50 is 84. But they said out of 250 students, how many would that be? So 84% of 250 is 210 students. Last question. If 13.6% of the students received a B on the final, how can you describe their scores? So picturing this being our scores, would the B's be to the right or to the left of the mean? To the right, right? My scores get higher as I move to the right? Okay. Is there a chunk of my graph that's about 13.6%? What interval would that be for my scores? Okay, so I'm somewhere in this chunk. Okay, so for part C, I'd say scores are between 165 and 180 would be your B's. Does that make sense? Okay. Now, with a normal distribution, you've heard teachers talk about curving their test. Okay, if a teacher truly curved the test, what they're saying is we have to take the scores that my students got and make them fit a bell curve. Okay, which means we're going to make some people get A's, but we're also going to make some people get F's. Yes? I don't curve your tests. You get what you get. All right? If everybody gets an A and a B, I'm not saying that lowest B score now becomes an F. That's not fair. Okay? All right, so are we good with using a normal distribution? Can we fill in our numbers for the percentages and the numbers at the bottom, going up in increments of whatever the standard deviation is? Okay. So your assignment, page 737, you're going to do 7 through 18 and 20 to 25.